welcome to the next phase of the interpretation of batch reactor data for reactor design. Now, if you recall that previously we have studied about the interpretation pattern of batch reactor data. Under this head, we discussed about the second order reaction, both for equimolar and non-equimolar feed. We developed the mathematical equation for nth order reaction for the prediction of batch reactor data. Now, in this particular lecture, we will discuss about the half-life order and varying volume reaction system. Both the things are very much important in relation with the batch reactor data and designing of polymer reaction reactors with respect to the product profiling. Now, for half-life method for reactions, now it is as the basic line suggests that it is the time required to achieve 50% of conversion or time required to reduce the concentration value of the reactant to reach just half the initial value. So, if we take the example of our previous reaction, that is A plus B is equal to P. Now, if we talk about the half-life pattern or half-life method, then it may become Ca, concentration of reactant A is equal to Ca naught by 2. So, at you can say the time t is equal to T half, this one. So, this is the initial concentration and this is the concentration after T half. So, the kinetic expression for nth order reaction will become 1 upon Ca n minus 1 is equal to 1 upon Ca naught minus 1 kT. So, this equation is representing the nth order reaction. This is the kinetic expression for this half-life prediction. Now, on putting the value of half-life of the reactant concentration in this equation and try to rearrange, then we found that this equation becomes 1 upon Ca naught by 2 to the power n minus 1 upon Ca naught n minus 1 is equal to n minus k T half. So, if we go for the rearrangement, (0.5) 1 minus n minus 1 upon n minus 1 k Ca naught 1 minus n. So, this is I can say my general equation for predicting this particular half-life pattern of this data. Now, this required expression for half-life of nth order reaction. Now, it is from the half-life expression that the half-life is the function of initial concentration and valid for all kind of n except n is equal to 1. If you see that if you put n is equal to 1, then the entire equation will spoil. So, the half-life of zero order reaction can find out on putting the values of say n is equal to 0 in zero order rate equation and to find out the value of T half at Ca naught upon 2k. Similarly, for second order reaction, if try to find out the T half, that will be 1 upon Ca naught k. And for the first order reaction, if we put the values, then Ca is equal to Ca naught upon 2 in kinetic expression for first order reaction. And if we found that T half is equal to 0.693 upon k, this is a very important result. Now, let us come to the last phase of this interpretation of batch reactor data, that is the varying volume reactor system. So, when volume V that is usually expressed in terms of a unit of a liter, and the volumetric flow rate, let us say that having this small v liter per minute of the reacting material is varying with the time in a reactor pattern or reactor system with the progress of the reaction. Then such type of a system they are referred as the varying volume reactor type of system, and it is applicable for both batch and a continuous type of reaction mechanism. So, I hope that this particular thing is understandable, that you are carrying out a reaction in this particular any kind of a reactor, and the volumetric flow rate and volume V, they are into the consideration, and during the progress of the reaction, the V and both the volumetric flow rate both are varying due course of time. So, we need to find out the various equation associated with this type of approach. So, let us have this thing to the consideration for the batch reactor type of system. So, we express the volume as a function of conversion in the previous equation by using the equation of state for varying volume batch reactor system. Now, the equation of state which attracts our focus, that is PV is equal to NT Z RT. Here other things are, let us put as equation number 1, pressure, volume, NT total number of moles, Z is the compressibility factor, R is universal gas constant, or sometimes it is referred as a characteristic gas constant, and T is the temperature of the system. So, this now if you see that if we try to find out the situation for time t is equal to 0, the equation of state we can write as P naught V naught is equal to NT naught Z naught R T naught. Remember, the P here we are representing P as a total pressure, which is represented in as a kilopascal. V is the volume of the reactor at time t, and already mentioned that it is having the unit of liter. Then NT is the total number of moles at time t, and Z is the compressibility factor, and we can put the value of R is equal to 8.314 joule per mole Kelvin. So, this naught represents the initial condition. Now, if we this is my equation number 2, and if you recall, here we represented the equation number 1. So, if we divide equation 1 by equation 2, then we may have this P V upon P naught V naught NT Z RT upon NT naught Z naught RT. So, if we cancel out these R, so V is equal to V naught NT upon NT naught, this is as a subscript, T upon T naught, P naught upon P, Z upon Z naught. So, this is the generalized equation. To write more clearly, it can be represented that V naught NT upon NT naught, T upon T naught initial temperature and the final temperature, P naught upon P, Z upon Z naught. Let us refer at this is equation number 3. Now, if we want to express the volume in terms of a conversion, so the total number of moles at any time of the reactor can be given as NT is equal to NT naught, change in the number of moles A naught XA. Let us put as equation number 4. So, if we divide this equation 4 with NT naught to both sides, then NT upon NT naught 1 NT naught XA. Now, here if you see that NA naught upon NT naught is YA naught, that is the initial mole fraction, not the mole, initial mole fraction of reactant A. Now, Nt upon Nt naught thus become 1 plus change in this pattern Xa, or in other words you can see that Nt upon Nt naught is equal to 1 plus epsilon A x A. Let us represent this particular equation as equation number 5. Now, here if you see that we use the term epsilon. Now, this epsilon is this delta Ya, where epsilon can be expressed as the ratio of change in total moles of reactant at full conversion to the initial moles of reactant feed to the reactor. So, this is again you can say it is a very crucial thing, and it is very useful for determining the efficacy of any particular reaction. Now, if you see that from earlier equation number 3, let us go back, this is the equation number 3 and equation number 5 which we discussed over here. So, if you see that equation number 3 and 5 for varying volume, these equations, and if you put Z is equal to Z naught for the gaseous system, the compressibility factor does not change during the reaction at the temperature and pressure. So, in that case we have V is equal to V naught 1 plus epsilon A x A T naught P naught upon P. Now, for constant T and P, and if you see that always we are looking for the extent of a reaction. So, epsilon A is represented as the extent of reaction. So, V is equal to V naught 1 plus epsilon A x A. Now, here the T is equal to T naught and P naught is equal to P. So, you see that these things are case sensitive. So, we need to take either certain assumptions or we need to assume the case, maybe the gaseous segment, maybe for some other segments. Now, as far as the concentration is in question, so for concentration of reactant A at any time, you may get the putting the values of varying volume in the concentration expression, Ca is equal to Na upon V. So, this particular equation, if you see that Ca can be represented as Na naught 1 minus Xa T naught P upon V naught 1 plus epsilon A Xa Tp naught plus, now this is the general equation, or we can represent it as Na is equal to Na naught 1 minus Xa, or V is equal to V naught 1 plus epsilon A Xa T upon T naught P naught upon P. Now, similarly, the concentration of reactant B or product C and D, if you are having the equation like this, this can be written as Cb is equal to Nb upon V, that is Cb naught minus B upon A Ca naught Xa upon 1 plus epsilon A Xa T naught upon T P upon P naught. Here you see that Nb naught upon V naught Cb naught. Similarly, if we try to write the equation for concentration of C, that is Nc upon V, this is equal to Nc naught plus C upon A Ca naught XA upon 1 plus epsilon A XA T naught upon T P upon P naught. Here NC naught upon V naught is equal to C concentration at 0 time. And last, if we try to write the C concentration of a D, this is represented as the number of moles of D divided by volume. C D naught, initial number of moles of component D, D upon A. A is the limiting reactant. Ca naught Xa upon 1 plus epsilon A Xa T naught T P upon P naught. Needless to mention that ND naught upon V naught is equal to CD naught. So, this, if you see that we are referring this particular reaction like this, B upon A, C upon A, C plus D upon A D. This is based on this particular equation. So, based on this particular approach, you can predict the things accordingly. Now, if I wish to predict the rate of reaction, in that case, when usually the epsilon, that is epsilon is not equal to 0. So, the rate of a reaction of a chemical reaction you can write as minus Ra 1 upon V dNA upon dt. So, at constant temperature and pressure and for the varying volume system, reaction system where we are considering that is epsilon is not equal to 0, then minus Ra minus 1 upon V naught 1 plus epsilon A Xa d Na naught 1 minus Xa upon dt. So, if we differentiate this particular equation with respect to T, then we may have minus Ra N A naught upon V naught 1 plus epsilon A Xa dxa upon dt, or you can write minus Ra Ca naught 1 plus epsilon A Xa dxa upon dt. This is my final equation, and this is the required performance equation for batch reactor system. Now, again another thing is that if we have the varying volume flow rate for flow reactor, so this type of similar equation for concentration term is formed for varying volume system for flow system as in the we observed in the batch reactor system. So, if we have the varying volume in liter per second, this is the ratio of a molar flow rate F, that is mole per second, to the concentration moles per liter. So, sometimes this volumetric flow rate is represented as F upon Ci. I is the ith component. Now, if the total concentration of Ct is in question, so the total concentration Ct can be written in the form of a volumetric flow rate and the molar flow rate, and the relate with the gas law. So, we can find that total concentration at any time t, this is Ct is equal to Ft upon this P upon ZRT. Let us put this thing as equation number 1. So, this is the total concentration at any time. Now similarly, the total concentration at the entrance of the reactor in the flow system, you can write like this, because at the entrance of the reactor, some of the concentrations may be put as 0 or not. So we can write the total concentration at the entrance of the reactor Ct naught is equal to Ft naught or P naught upon Z naught RT naught. Let us refer this particular equation as equation number 2. Now, if we divide these two equations and putting the negligible change in the compressibility factor, that is represented as Z is equal to Z naught, and if we try to rearrange, and then we find that this is Ft upon Ft naught, P naught upon P, and T upon T naught. So this is my equation, and let us put this equation as equation number 3. So if we talk about the flow reacting system, the total flow rate, if we sometimes we may require the total flow rate, this can be written as Ft is equal to Ft naught plus Xc. This is equation number 4. This is now here Ft is the total molar flow rate, that is represented in liter per minute. Then Ft naught is the initial molar flow rate, because we are changing this flow rate or varying flow rate we are considering to question. Then delta is equal to d upon A plus C upon A plus minus B upon A minus 1. Now here minus sign is put just to represent that both these reactants are being consuming in due course of time, and Fa naught is the initial molar flow rate of reactant A into the reactor system. Now we have already from these above equations. Now if we divide the equation, that is the total molar flow rate, by say Ft naught in both the side of this particular equation, then the things become like Ft upon Ft naught is equal to Ft naught upon plus delta Fa naught upon Ft naught Xa, and this can be represented like this: Ft upon F T naught 1 plus delta Yi, mole fraction of A naught into Xa, and upon rearranging this Ft is equal to Ft naught 1 plus epsilon A Xa. We can put this as equation number 5. So this here Fya naught is equal to Fa naught upon Ft naught, and epsilon A is equal to delta Ya naught. So these are the some of the referencing things. Now from this equation which we discussed, and on rearrangement, we can have this naught Ft naught 1 plus epsilon A Xa upon Ft naught P upon P T upon T naught. So we can represent like this: V naught 1 plus epsilon A Xa P naught upon P T upon T naught. Now this is the required equation for volumetric flow rate in varying volume system. So this is again a very, I can say this a very important relation which we developed in due course of time. Now if we see the concentration effect because we discussed about the varying volume, we discussed about the other factors. Now for concentration terms, the concentration terms can be described now from these relationships which we discussed in the previous slides, and similarly we can write the concentration term for all reactants and other product terms. So, if we would like to have the concentration of any species which can be written as, for this particular equation, we are taking this particular equation into account, A plus B upon B, C upon A, C plus D upon D. Now, here this is my master equation, or sometimes it is referred as Ci Fi upon P naught into T upon T naught. Now, here 1 plus epsilon A x A P upon P naught, T naught upon T. Now, if we see about the reactant concentration A, then C A is equal to F A naught 1 minus x A 1 plus epsilon A x A P naught upon P, T upon T naught. As we know that F A is equal to F A naught 1 minus x A. Now, here then C A is equal to C A naught 1 minus x A upon 1 plus epsilon A x A, and that becomes the P naught T upon T naught upon T. Now, similarly, if we wish to have this type of equation for reactant B, so let us put this thing in this way. F B is equal to F B naught minus B upon A F A naught x A. Now, C B is equal to B upon A F A naught x A upon mu naught 1 plus epsilon A x A P upon P naught into T naught upon T, or C B is equal to F A naught F B naught upon F A naught minus B upon A x A, and this is 1 plus epsilon A x A and P upon P naught T naught upon T, or C B is equal to C A naught F B naught. All these things are with their usual interpretation, B upon A x A into 1 plus epsilon A x A P upon P naught T naught upon T. So, similarly, we can write for concentration of C. This is C A naught. Now, here we are putting the plus sign because the C is being generated in due course of time upon 1 plus epsilon A x A multiplied by P upon P naught T naught upon T. Now, here F C is equal to F C naught plus C upon A F A naught x A. So, by this way we generated these mathematical equations for prediction of varying volume concept. Now, at last in this particular segment we discuss the varying volume concept. and with the taking the concentration into cognizance, and we developed the various equation associated to this for the interpretation of batch reactor data. Now, if you wish to have further reading, again we have listed couple of references in the reference slide, and hope that this particular lecture you enjoyed a lot. Thank you very much.